Example number 4. Again, we're going to talk about continuous functions, and we're going to sometimes we'll do composite functions, which are like combinations, one function within another function. This is a triple whammy of functions. There's really like 4 functions in one. So I want like the absolute value of x times sine of x all over x squared plus 2. And so what we're asked to show it's continuous.
How is that funny?
Well, because I'm looking at it, like whoever wrote the book was like, what more could we possibly put in this one function? So to show continuity, we basically have to think about restrictions in the domain. Now in Algebra 2 and Algebra 3, we talked about only 2 cases. One was negative square roots, can't do that, or even roots. We want to expand on that now that you guys understand what you're doing. So no negative even roots. You can't take the even root of a negative number. The other restriction was you can't have 0 in the denominator. And a third restriction we don't talk a lot about is like natural log. And really, truthfully, there are other restrictions, but those are the most common ones, and we're going to stick with those, okay? So since we're in courtesy mode, I'll go ahead and graph this on the screen. And basically, before I graph it though, we don't have a square root, we don't have a natural log or a logarithmic function. We do have a denominator. What does x squared need to equal in order for this denominator? In other words, what can make that statement true? What value of x can make that statement true? Well, here's the thing. If we solve it, we end up with x squared equals negative 2, or x equals plus or minus the square root of negative 2. And that's not a real number solution. So there are no domain restrictions. So the domain of this thing is from negative infinity to infinity. All real numbers, right? So really it should be continuous. Now the other thing we got to check is make sure that it's an actual function and that all the y values can be defined. But if I could plug in an x number for just about anything, I should be able to get a y value, right? So the final test would be just to graph it. And so if I wanted to graph this thing, oh, I already had the calculator up. It's a little complicated, but not really. I'm going to come in here, clear out all my graphs. And so I hit second, catalog, ABS for absolute value comes up first. Then I want another set of parentheses so I can plug in sine, or x times sine of x. Whoops, hit the wrong button there. Oh man, that's crazy. It's going all over the place. Sine of x all over, start parentheses again, x squared plus 2. And I'm going to zoom in to trig. So now whenever we do the absolute value of sine, it's going to give us all positive values. So, well, you'll see. I'll hit graph. That's what it looks like. And as x increases, right, as this approaches positive or negative infinity, the bottom kind of blows up and gets a big number on the bottom, so there's a dampening effect on the oscillation. It isn't really an oscillation, it's a pattern that repeats itself. But basically the humps get smaller and smaller, right, as we go closer and closer to positive or negative infinity. So the question originally was, is it continuous?
Yeah.
Well, yeah, but how could I prove that?
Graph it.
Well, there's a theorem in your book, so graphing it kind of proved it, but I'd have to look at the graph for everything from negative infinity to positive infinity. So there's a theorem, theorem 7, and I'm not going to test you on like which theorem it is, but it's something that you need to know. If f is continuous, okay, at c, some value c, and g is continuous at that same value c, then g of f is continuous at c. Okay? So what does that mean? That means if I think of this thing as g is equal to the absolute value of x and f of x is equal to x sine of x all over x squared plus 2. Well, both of those functions are continuous. So when I write the composite function, which is really this, when I write the composite function, that's continuous as well. That's pretty much it. Anybody have any questions on that one? Well, we know that this is continuous because it's one of the 12 basic functions. We know that this is continuous because, well, the x squared is always going to yield a positive value. Well, I take that back. If I plug in 0, the x squared might yield nothing, right? But nothing plus 2 will give you a value on the bottom of the denominator. So this will never ever be undefined at any point for any value of x that I plug in. So it's continuous.